Part 2 of vector calculus applying projectile motion and in a plane, and you might hear a plane in the background. Yep, that's a different sort of plane. We're looking at some examples, and I intend to do 3 worked examples of increasing difficulty level as we go. So the easiest one first, particles projected from a point, ground's nice and horizontal, that helps, and we've got a launch speed 50 meters per second. We've got angle of projection or a launch angle, same thing, angle of projection of 30 degrees. I and j are the unit vectors, horizontal and vertical as normally we see, and a good old neglection of air resistance, so that helps. And we've got 4 things to do there. The initial velocity vector. Okay, now in the previous video we saw there was actually for something launched at and we're launching at the origin here. Okay, so that helps. Okay, the third example won't be launching at the origin, by the way. So we saw previously that we have for the velocity, the initial velocity is u equals u cos theta I plus u, oh no, look what I did, abracadabra, and it's fixed. There we go. So we saw that in the previous video, and the reason for that, by the way, is when we're launching something on a parabolic journey. Okay, so if we take it nice and simple, okay, this thing will travel in a parabolic path, projectile motion. At launch we've got, say down here, we've got initial velocity, which is a straight line vector. Just that instant of launch, it is a straight line. And there's trigonometric reasons why it's u cos theta I plus u sin theta j. You can do a little right angle triangle in there, and we can see that if we're remembering that this u here is a magnitude of vector u, and you can see that by breaking that vector down into its components with the use of trig. We've got a right angle triangle, and so we can see that the vertical component is indeed u sin theta and the horizontal component is u cos theta. So we sub those values in from the given information, and these cos 30 and sin 30 are exact values, so that's helpful in the computation. So it's 50 times root 3 over 2, so it's, could write that out in full. You don't really need to, you should be fluent here. 50 times root 3 on 2 I plus 50 times a half, whoops, 50 times a half, Mr. Stylus and tablet. 50, now I've gone and written, I didn't want to write a decimal, I wanted to use a fraction, darn it. I'll fix that up. Hey presto, that's better. Alright, so we have 25 root 3i plus 25 j meters per second. In part B we've got to find the general velocity vector, so that's v of t, or if you like r dot, and we have to go from what we know, and the thing we know is that a equals negative g j, or we could use 9.8 instead of g if you like, but the cool people tend to go with g. So you take the integral negative gt j plus c1 vector. We can find that the constant is in fact the same as this initial velocity if we sub in t equals 0. Okay, so through substitution of t equals 0, we can find that. So that is known, it's established, and look at that, tilde. So we can sub that into the greater expression. So that means what we're looking for, the velocity, is 25 root 3I plus 25 minus GT J meters per second. Okay, third part, the position vector at time t, so it's the general position vector r of t. So is the integral of what we just had. That's an r. Okay, and this throws back to earlier videos we've encountered that we've watched. Alright, so we get that there, and for the vector C2 we know that it's launched at the origin, so we know that it's 0i plus 0j. If we were to do the substitution, we could easily show that. Okay, and that's what we get for our final answer for part C. And lastly, we need to find the Cartesian path. Okay, the path, sorry, which is our Cartesian equation, I should say, rather. Okay, now we've done this with other scenarios before, so we proceed as we have in the past. We remember Cartesian is y versus x. We use information based on the position vector, of course, so r will equal, it's keeping things really lean and mean, r is xi plus yj. And from those we can get parametric equations like so. So there are parametric equations, and then we need Cartesian, so we need to make a substitution. You could modify equation 1 there, so we could call this a modification of 1, which maybe you might want to call it 1a. Okay, and just use t as the subject. That makes the substitution much easier to see. So it's x over 25 root 3. So in equation 2, wherever we see x, we can replace it with, so wherever we see t, we can replace it with the result of equation 1a, which is x over 25 root 3. Let's do that now, and we get 25 times x over 25 root 3 minus g over 2. I'm going to separate the g over 2 a bit, and then the t squared is the x over 25 root 3 all squared. Those 25s there cancel. So we have y equals x on root 3, or 1 on root 3x. Okay, so minus g over 2, now that would be x squared, applying index laws. Now on the denominator we have 25 squared times root 3 squared, which is just 3. Okay, it's 625 times 3, and that is 1875. So we have x squared over 1875. Okay, tidying it up, we should get a quadratic too, right? Because we got a trajectory here, we've got projectile motion parabola. So yes, it looks like we're heading to a reasonable answer here. So it would be root 3 on 3x, just rationalizing the denominator because that's nicer. And we have g, remember g is a constant, gx squared over 3750 So that says negative root 3 on 3x minus gx squared on 3750 is our Cartesian equation. Example 2, golf ball is hit so that it leaves the bunker at 35 meters per second, angle 20 degrees. That's your launch angle, angle of projection. State the final velocity of the ball, and we've got 4 other things to do after that. So, part A, the initial velocity vector, which is that, or you might want to use U or V naught. 35 cos 20i plus 35 sin 20j, evaluating that because they're not exact values. 32.9i plus 12j meters per second, just like in the previous example. Part B, find the velocity of the ball as a function of time. Okay, just getting rid of that errant comma there, that bothered me. I don't know what that comma was doing there. Find the velocity of the ball as a function of time, so v of t or r dot. Okay, so part B, very much like the previous video, so previous example on this video. Whether we use a formula or whether we just go from first principles, and that's what I'll be doing, first principles, we still get the same answer. So there we go, and we get negative gt plus c1, the constant of integration. But at t equals 0, we get the following. We get, from previous, we've got 32.9i plus 12j is the same as when we substitute into here, negative g times 0 plus c1. So c1 actually equals this vector here. So we know our full equation now. You should be getting used to doing that step. And you should know what to expect each time you do it. So we've got positive 32.9i for the whole vector plus 12 minus gtj meters per second. Maximum height now, we've got to think about what that means. What's the significance of maximum height the ball reaches and the location of the maximum height from the bunker. So what is the maximum height and what is its location? Where is it in two-dimensional space? Okay, so what happens when a projectile hits maximum height? The velocity in the y direction will equal 0. So you've seen as you've thrown something, its vertical height is when it hits its vertical maximum height, its vertical velocity is 0. It's still moving forward in the I direction, but it's for that moment it stops in the j direction. So that's basically what we got there. And then just using the equation part of it, so that means 12 minus gt equals 0. Okay, and so gt equals 12. Remember g being a constant, and t equals 12 over g. And if you needed a decimal, 1.225. To find the location, we use a position vector. Okay, now we don't actually have that yet, so we've got to derive that too. So to get r of t, we have to take the integral of the velocity. We get that, like we've seen previously. Now at the initial position, which is the origin, okay, this one's straightforward in that regard. At time equals 0, we substitute in t equals 0 for all these terms, and they'll all be knocked out as 0 because they all contain some sort of t parameter in them. So that means this constant C2 also equals 0, just like we've done previously. And so that means therefore r of t is indeed that function with a constant of 0 on it. So 32.9 Ti plus the rest of it there. And we can go back now and substitute 1.225 in there like we wanted to before and get an actual value, a location position. So it's at 40.3i plus 7.35j meters. It's its location where it hits its max. Next we had to find the time the ball is in the air in part D, which is often called the time of flight. Now because it's launched and it launches and lands at the same level, it is simply the second time that the vertical component of the position is 0, because it needs to be in line with the origin. So just grabbing the j component from the position vector above, and we've got to solve for that. It's a quadratic, so we may get two solutions, but we've got to interpret it carefully. So we've got, I missed a t there. There we go. Now don't just jump straight to the quadratic formula, okay? You can do it this way. And the null factor law still works. So t equals 0, or we've got 12 minus g on 2 t equals 0. Now this one here is not going to be the answer. We don't want this answer because that's at launch there. So that's not the answer we want. It's based on this one here, and we've got 12 is g on 2 t, so t is 12 divided by g times 2 is 24 over g, which it was rounded to 2.45 seconds. So its time of flight is 2.45 seconds, because the clock was reading 2.45 when it hit the ground. So that's from launch to landing is 2.45 seconds. Last part is the range, okay, which is the horizontal distance, and again the launch and the landing heights are the same, so that makes it easy. We just want the x distance from the origin out to where it touches when it hits. So we've got x of 2.45, 32.9 by the 2.45. That's 80.6 meters. Last example, we've got a difference here. We can see that the height at which it's thrown and the height at which it lands are different. Okay, so it's a bit like this scenario here. Okay. Alright, so that poor old Steinway, that is dead now, and Willie scored a point. The thing is that you notice that the launch height and the landing height are different, and that's a variation on this sort of question. When we sub t equals 0 into this given equation here, r of t, we'll notice that r of t, or r of 0, will equal 1 j. So that's 1 meter. So it actually is thrown a meter above where it lands. Okay, so it's going to launch there and basically travel parabolically okay, and then keep going. That's slightly exaggerated, but you get the idea. So if it landed there, it'd be a nice symmetrical parabola, but it goes a bit further. And sorry, that should maintain that curvy shape. It wasn't the best drawing. So we write our answer in, and we get 1 meter above the origin. Part B. Velocity vector is what we've got to find, and we just take the derivative of the given vector r of t, so we get 4.9 I plus 22 minus 9.8 t. Now that should be looking sort of familiar to you now, right? 9.8, that's g, right? Now the initial speed, it's not velocity, it's speed, okay, is the magnitude of the initial velocity vector. So to get the initial velocity vector, we can use the result from the previous line, and it's when we substitute 0 in, and we get this. That'll be 22 minus 0j, so it'll just be 4.9 I plus 22j, and the speed is the magnitude of that, so we apply our definition of magnitude, our process for finding the magnitude. Okay, it's 22.54 meters. Now the launch angle, I missed something. Oh no, sorry, I'm looking at the wrong question. That's what we're doing. Okay, launch angle, we can use trig for that, like I mentioned earlier. So to get theta in that little right angle triangle, we can use our trig. So the x component of the initial vector u, initial velocity vector u, okay, so we can look at that and use some trig. So to find theta, we could use tan theta, so tan theta opposite over adjacent, because that's what you try and do, use tan theta, and we know that one's 4.9 over 22, and then taking the inverse tan. Whoops, I've just realised I've got the fraction upside down there, because that's opposite and that's adjacent. So I've got that upside down, try 22 over 4.9. Apologies. There we go. 77.4 degrees is your angle of launch angle, projection angle. Find the speed and angle at which the project strikes the ground as part D. Okay, so when the y component of the position vector is 0, that's when it strikes the ground. So we use a quadratic formula on there, or if it's tech active, you could use graphics calculator. So we get two values there for when it strikes the ground. The first one's invalid, okay, because t, one of the reasons t has to be at least 0. So that's the one we want, and the velocity it's going at that point is at 4.535 seconds is 4.9 I minus 22.44 j, which makes sense because it's going a mixture of that way and that way, hence the negative j. So it's finding the magnitude after we found the vector, 22.97 meters per second, nearly at the end. So for the angle of impact, it's coming down. We need to interpret this carefully here. It's coming down. We know it's velocity. We got components. So we have to be careful. We're going to use the same reference as we do for launch angle. Remember, launch angle, when something launches, it's basically that angle in there. So if we look at this here, we'll get to get the true angle, or after we'll get a big angle there, or like a reflex type angle, or basically you could use the complement, the negative of it. Okay, once we find this, we can just write the negative of it there for that. So angle of impact So using our little triangle there, we've got 4.9 in that direction using the velocity, and 22.4 there, its magnitude. Okay, the negative's irrelevant here, and we've got opposite over adjacent, so we're going to use tan there. So it's going to be the inverse tan of 22.4 over 4.9. Oh, I forgot to write inverse tan. So we get 77.6 degrees, and we equate that as with reference to I, or the same as the initial reference for the initial launch angle, which is going anti-clockwise from I. It's negative 77.6 or 77.7. Theta impact, I'll just put theta sub I equals negative 77.7 degrees. Again, because we're looking at, in fact, going clockwise to get that. Okay, so it's either that or you go 360, take 77.7 away. Okay, it's not regular old 77, because that would be something like that. Okay. Last part of the epic video, total distance from the launch site. Now remember, they're not on equal ground vertically, and it's gone a distance horizontally, so it's actually going to be a displacement job. So what we want to do is compare that, and at the impact point, which I'll just get the number again, 4.535 seconds. We said that was J, and this, we use the given vector and substitute the value for T in, like so. Okay, I get that, and I get that as the final answer. Might have made an error, I'm not sure, you might want to just double check. I haven't entered anything wrong, but there we go.